morning children, and welcome back to your chemistry class. Today in this video we are going to talk about the trend in the chemical reactivity of the 13 group elements, right? So elements of this group 13, let me write down of group 13 we were talking about, right? They have 3 electrons in the valence shell, which are used by these elements to form 3 bonds, and thus they show oxidation state of what? +3, right? But this is not found, or you may say that thallium is exceptional. The 3 bonds are not found in thallium, right? So in this +3 oxidation state, element of this group, they are expected to form what? They are expected to form covalent bonds, as I told you. Now what are the reasons for forming covalent bonds? Firstly, the sum of the first 3 ionization enthalpy being very large, the formation of trivalent ion is not favored, right? So I write it down over here. The sum of the first 3 ionization enthalpies being very large, formation of what I told you, the trivalent ions is not favored. Is this point very clear? The second point, the second reason why covalent bonds are formed is according to Fazan's rule. If you remember, the small size of the ions and their large charge of +3, they favor the covalent bond. Clear? Favors covalent bonding. 2 points are clear. Now the third important point is the electronegativity value. Okay, the electronegativity values of this group 13 are higher as compared to group 1 and 2 elements. Is this clear? Therefore, when these elements, when they react with other elements, the electronegativity difference will be small, right? And this is going to favor what? Covalent bonding. So I hope these 3 points are very clear to you. Now, talking about boron. Boron, we know that due to its small size and high sum of first 3 ionization enthalpy, it does not lose its 3 valence electrons to form the trivalent ion, and therefore borons, they do not form ionic compounds. Okay, therefore boron does not form what? Ionic compound. This point is clear. Once again, should I repeat? What am I talking about boron? Boron, it has small size, first point that I said to you, and it has a high sum of first 3 ionization enthalpies. Let me write it down properly. Ionization enthalpies, and they do not, therefore do not lose its 3 valence electrons to form B3+, right? Therefore boron, they do not form ionic compounds. Therefore boron do not form ionic compounds. I hope this is very clear. Instead, it always forms what? Covalent bond, as I have listed every point about why the group 13 element they can form, that is boron can form covalent compound. Followed? But when we go down, that is from boron to aluminium, what are we going to see over here? The sum of the first three ionization enthalpies of aluminium, they considerably decrease. So what will happen? Consequently, this aluminium, it is able to form what? Aluminium, the trivalent ion. So over here, aluminium is highly electropositive metal, and its compounds such as like aluminium trifluoride, or you may say aluminium sulfate, right? They form ionic compounds. They form ionic compounds. Whereas if you talk about aluminium chloride, or if you talk about aluminium bromide, alright, they form covalent compounds. What do they form? They form covalent compounds. Now, once again, I am going to tell you why do these elements they form covalent compounds and why they form ionic compounds. Now, just now as I explained you, according to Fazan's rule, what does it state? That with increase in size of the anion and with decrease in the size of cation, what will happen? The ionic character of the compound decreases while the covalent character will increase, right? So here, if you look at these two examples like aluminium trifluoride and aluminium chloride, the cation is same. The cation remains the same over here in both the compounds, but the size of the anion is now going to decide the nature of the compound, whether it is going to form ionic or covalent compound, right? So over here, if you see for fluorine and chlorine, the chlorine being greater in size than fluorine, so chlorine is going to form a covalent compound while fluorine is going to form the ionic compound. Okay, so like aluminium, many other compounds of other elements such as your gallium trichloride or indium trichloride, they are also covalent, in anhydrous state. Okay, they are also covalent in anhydrous state. I hope till here it's clear. Now, due to poor shielding effect of intervening your d and f orbitals, the increased effective nuclear charge, it holds the ns electrons tightly, and thereby this restricts their participation in the bonding, which is also, as I told you earlier, called as inert pair effect, right? So I'll write it down over here. Due to poor shielding, effect of d and f orbitals, the increased effective nuclear charge holds the ns electrons tightly, and hence their participation in bonding is restricted. Okay, this is also called as what? Inert pair effect. Thus in gallium, indium and thallium, both +1 and +3 oxidation states are observed, and the relative stability of +1 oxidation state progressively increases for the heavier elements, right? Now since the ions of +1 oxidation state, they are much larger than the ions of the +3 oxidation state, the compounds in +1 oxidation state, they are more ionic, clear, than the compounds of +3 oxidation state. I hope this is clear to all of you. Now in trivalent state, most of the compounds being covalent, they are hydrolyzed in water, right? For example, the trichlorides on hydrolysis, they form tetrahedrals. What are the tetrahedrals? Like MOH, or I should write it down like this, MOH 4, and this will be minus. Okay, it is found in this over here. This M, the hybridization of this is sp hybridized, right? For example, like BCl3 on hydrolysis, it forms the tetrahedral ion. What is that tetrahedral ion? Boron, that is M, which will be the sp hybridization, OH4 minus. Clear? This ion is going to form. Why? Because boron, due to the absence of the d orbitals, cannot expand its covalency beyond 4. Correct? Aluminium chloride. Now for example, let's talk about aluminium chloride. The aluminium chloride, in acidified aqueous solution, it forms octahedral ion. What is octahedral ion? AlH2O6 3 minus ion will be formed when in acidified aqueous solution, right? In this complex ion, the 3d orbitals of your aluminium, they are involved, and the hybridization of aluminium over here is found to be sp3d2 hybridized. I hope it's very clear to all of you. Just now we are going to discuss all this in detail also. Now let's talk about the Lewis acid character also in trivalent state. Okay. So in trivalent state, the number of electrons around the central atom in a molecule, like for example, I'm talking about say boron fluoride or maybe aluminium chloride and so on, the compounds of these elements will be only 6. Now due to the presence of the p orbital, they can accept a pair of electrons to complete their octet, and thus they act as Lewis acid, right? Once again I repeat, due to the presence of which orbital I said? Due to the presence of p orbital, they can accept the pair of electrons to complete their octet, and therefore they are good, or they act as Lewis acids. For example, the trihalides of boron, I'll show it to you over here. They readily combine with the Lewis bases. Lewis bases are what? The electron donors. And for example, your ammonia is your electron donor, or you may take fluoride ion and electron donor and so on to form the donor acceptor complexes. So let's look at one example over here. Like for example, as I said with ammonia, let me show it to you with ammonia. So it has a lone pair, okay, and this is a Lewis base, this is the Lewis acid, right? So what is it going to form? This will be the donor and they will be the acceptor. So here it's going to form NH, B, F, F and F. Clear? So boron trihalides, they cannot extend their oxidation number beyond 4 due to non-availability of the d orbitals. I hope till here it's very clear. So the relative Lewis acid strength of trihalides of boron, we can understand the order of them. That is, I must have told you yesterday also in the previous video, boron, bromide, followed by boron chloride, and least will be that of boron fluoride, right? Due to the presence of only 6 electrons in the valence shell of boron halides, they are also, what are they termed as? Electron deficient compounds. What did I say? Due to the presence of, I'll write over here, due to the presence of only 6 electrons in the valence shell of boron halides are called electron deficient compounds. Is this point very clear to all of you? I make a star over here so that you understand this. Now, after this, we are going to study about some important properties of group 13 elements, and this was all the basis of what now I am going to explain you. Okay, so let's begin with the first point, that is, we'll talk about hydrides. Elements of boron family, they do not directly combine with hydrogen to form the hydrides. Okay, do not directly combine with hydrogen to form hydrides. However, number of these hydrides, they have been prepared indirectly. Clear? Hydrides of boron, their general formula is BnHn plus 4. So if B is 1, H will be 4. BH4. They are, what are they called as? They are called as boranes, right? And they are highly stable and they have high melting points also. Stable and high melting points. Whereas the hydroborons, like their general formula is BnHn plus 6. What are they called as? Hydroboranes, right? And they are generally unstable and even they have low melting points. The simplest borane that I had already told you, it is diborane, and the formula is what? B2H6. Diborane, B2H6. Okay. Next, let us talk about oxides and hydroxides. Now, over here, group 13 elements, they form trioxides, that is M2O3. So, as we move down the group, there is a gradual change, right, from acidic to amphoteric to basic nature of the oxides and even the hydroxides. Why is it so? Because as we go down the group, the atomic size is increasing and the electronegativity and the ionization potential of the element goes on decreasing, right? So as a result, the bond that is formed between M and O in M and OH, it goes on decreasing. goes on decreasing. What is the reason? Because the atomic size is increasing and the electronegativity and the ionization potential decreases as we go down. Thus, the decreasing order of the bond that I can show you over here is what? Firstly, with boron and oxygen, the bond is stronger than aluminium and oxygen, lesser in gallium and oxygen, still lesser in indium and oxygen, and least will be in thallium and oxygen. So consequently, what are we going to see? The bond between the two, the element and the oxygen, it is broken easily, leading to the formation of your positive ion and the OH ions, right? Hence, the basic strength goes on increasing as we go down the group, and the acidic strength goes on decreasing. So, the basic nature increases and the acidic nature decreases. So, what did I tell you? First, they show the acidic nature, then the amphoteric nature, amphoteric followed by basic nature. So this is what I was telling you. The basic strength goes on increasing, basic strength is increasing, and acidic strength is decreasing over here. Hence, the decreasing order of the acidic strength in hydroxides and in oxides, let us understand over here. So if I have written this over here, accordingly we can study. This is more acidic in nature. Then we have Al2O3. This is amphoteric in nature. Then your gallium trioxide. This is also amphoteric. Then we come to indium trioxide. This is basic. And lastly, your thallium oxide. Thallium oxide. This is a strong base. So I'm writing it down over here also. This is acidic. This is acidic. This is amphoteric oxide. Acidic oxide, amphoteric oxide. This is also amphoteric oxide. Okay. This is basic. And this is a strong base. This was with respect to your oxides, right? Now let us talk about hydroxides. Now I'll show you the decreasing order of acidic strength in the hydroxides, right? For example, BOH, this is stronger, this is acidic, right? Then aluminium, this is amphoteric, then gallium, the bonding, it shows amphoteric hydroxide, this then indium, basic in nature, and the most strong is your thallium. This is strong base. Okay. So I hope till here everything is clear. So elements of group 13, they, as I told you, also form the hydroxide. So hydroxides of what type? They are MOH3. So now when boron, it is burnt in oxygen, what it is going to give? Boron, when it is burnt in oxygen, it will give us B2O3. This is called as boric oxide. What is this called as? Boric oxide. Let's balance this. This will be 2, 4, 3. Right. So this is called as boric acid. This is also a good dehydrating agent. I'll write over here dehydrating agent. It is a very good dehydrating agent also, right? Now this reacts with water and further it is going to form orthoboric acid, that is B2O3 when combines with H2O, it forms H3BO3. This is called as what? Orthoboric acid. Is this clear? Now, this boric oxide, which is also an acidic oxide, it dissolves in alkalis and it forms borates, right? So B2O3, which is an acid, reacts with a strong alkali, that is NaOH, and it is going to form what? A borate, that is sodium borate plus H2O. So balance this equation also. This equation is also to be balanced. Okay, I forgot to balance it. 2. It is balanced now. Okay, let's balance this also. This is 6, 2, and this becomes 2. Okay, I hope this is clear. Now, when aluminium is heated in the presence of oxygen, do we know what it is going to form? It forms aluminium oxide. Okay, aluminium, 4 parts of aluminium reacts with 3 parts of oxygen and it forms Al2O3. It is amphoteric in nature, we know that, and it is soluble in both acids as well as in bases. So Al2O3 combines with, let's react it with H2SO4. So it is going to form Al2SO4 whole thrice plus H2O here, and it is also going to react with, it is amphoteric, and this was acidic in nature. This was acidic, right? This is amphoteric. So Al2O3 can also be treated with strong alkali, 2NaOH, and it is going to form what? Sodium meta-aluminate, if you remember, 2NaAlO2 plus H2O, right? Now, this Al2O3, also called as alumina, it exists in many forms. One of its form is corundum. It is extremely hard and it is used as an abrasive and as an ore as well, right? So this was all about your reaction for the group 13 boron and aluminium with oxygen to form oxides and with water to form hydroxides. Talk about reaction with air and water. Now, boron reacts with oxygen only on heating. It does not decompose cold or hot water. Clear? I'll write it down over here. Boron reacts with oxygen only on heating. I hope you understand this. Then does not decompose cold or hot water. Clear? Now let's talk about aluminium. Now let's talk about aluminium over here. So aluminium, it reacts readily with air and also decomposes your water at ordinary temperature, right? Why? Because it has a very strong affinity and it forms a protective layer of the oxide to further protect it from any other further action. Okay, so what did I tell you about aluminium? Aluminium readily reacts with air, first point. Second point, what did I say? Decomposes water at ordinary temperature to form a protective layer of its oxide. You can say 4 aluminium reacts with oxygen, 3 oxygen to form Al2O3 as I wrote earlier. Also over here then aluminium can also react with nitrogen. On heating it forms Aln, right? Now to tell you, gallium, indium and thallium, they do not react with nitrogen to form nitrides. Okay, gallium, indium and thallium do not react with nitrogen, do not react with nitrogen. Clear? Okay, then talking about aluminium with water, as I have written over there. Let me also, okay, now talking about aluminium with water. Aluminium plus water, they react to form aluminium hydroxide and hydrogen gas is given out. Then gallium and indium, they are not attacked by water, whether they are in the hot form or in the cold form. Whereas thallium, it is attacked by water and the moist air. So we can write over here 4 parts of your thallium. They react with water in the presence of oxygen to give us thallium hydroxide. Now fourth one, reaction with acids. Reaction with acids. So boron, it remains unreactive towards acids, right? Even if we talk about bases also, let's talk about acids and bases together over here. So we can say that boron unreactive towards acid and bases, right? Even at the moderate temperature. Now let's talk about aluminium. It dissolves in acids and what does it give? It gives, now here I will use HCl. I had already used H2SO4. Here I will show it to you with HCl. 6 parts of HCl, they will combine to give us AlCl3 plus 3H2, right? Aluminium also reacts with alkalis, as I have already told you. It is an amphoteric metal, so it will react with NaOH. 2H2O gives 2NaAlO2 metaluminate, plus because we are using aluminium, so it is going to give out hydrogen gas, right? Now let's talk about fifth one, with halogens. These elements, they react with halogens to form trihalides, except for thallium, right? So I'm giving you a general formula over here. 2m plus 3x2 is going to give us 2mx3, right? So we can see over here 2 boron plus 3 chlorine is going to give us 2 boron chloride. Or if you want to use another halogen, it can be 2 boron plus 3 bromine will give us 2 bromide. Clear? Now the structure of the boron trihalides are always planar triangular structure. Boron halides, they have planar triangular structure. Clear? And over here, boron, they show sp2 hybridization, or they are sp2 hybridized. Is that clear? And again, in sp2 hybridized, boron has empty p orbital. How to show it to you? Let me show it to you over here. Now suppose boron at the ground state. Okay, boron atom I am showing you in the, this is the, if I show you the ground state, then do you remember this? I had taught you earlier also. So this is 1s, 2s, 2p. I hope I'll be able to make it. No, make it a little bigger. So if it is 5, then 1s2, 2s2, 2p1. Clear? Now in the excited state, boron atom, in the excited state, what will happen? Okay, one, and this will go next one to the next shell. So what did we see here? The 2p vacant orbital, isn't it? So what kind of a hybridization is it trying to show you? It is going to show you sp2 hybridization. Clear? So what kind of a structure is it showing you? It is showing you a planar triangular structure. It is showing you a planar triangular structure is shown to you. I hope this is very clear to all of you. Okay. Further we move with aluminium. It also combines with chlorine to form aluminium chloride MX3. Okay, balance it 2, 3, 2. Determining the molecular mass of aluminium chloride, it indicates that actually the aluminium chloride, it exists as a dimer having the molecular formula what? Al2Cl6, right? So here I am also going to show you the structure of this dimer of aluminium. See the structure over here. I'll draw it for you. Cl. This is. Now look at the angles and the bond length that is formed between the aluminium and chlorine. Firstly, the angle over here, this is of 101 degree, okay, 101 degree, right? And the angle over here, this aluminium, this is 79 degrees. Clear? So this is clear. This is also 101 degree and this is also your 79 degrees. Now let us look at the bond length between this chlorine and aluminium. It is 206 pm, and the bond length between this chlorine and this aluminium, it is 221 pm. Okay, the angle of chlorine aluminium chlorine, this is 118 degrees. Here also this is 118 degrees. So this is the dimeric structure of aluminium chloride. Clear? So with this I stop over here. In the next video I shall be discussing about the compounds of boron and aluminium also. Thank you.